finals cube. The last day of class, which will be Tuesday, whatever, 2 weeks from today, we'll do a review, and Stefan typically does a review as well, where he goes over the previous, an old final. I suspect you plan to do that again, Stefan?
Yes.
Yes?
This is a change of topic. I couldn't get LP Soft to download on Mac properly. I don't know if there's anything special you have to do.
Anyone have to do anything special to get LP Solve on a Mac?
You have to run it through the console.
It's not working.
You do have to run, there's no like,
There's no
GUI.
IDE as far as I can find, but there is a tutorial about how to run it on the console on the website.
Okay, thank you.
Well, isn't there like an online LP solver that also gives you like duals and all that too?
I suspect.
You can look at Desmo's calculator, and they have a linear graphing utility as well.
Okay. Okay, so that's where we stand. Any questions or problems? Other questions or problems? Okay. Let me find where I want to do here. So I had projector problems at the start, so it sort of got to take me a second to get set. Remember where we were. Okay, so at the end of class last time, we were talking about reductions. And I said it then and I'll say it again. This diagram here, which isn't completely revealed yet, some students like to look at it and think that it's complicated and impossible to understand. It's not. It's actually pretty straightforward. The idea is, I'm trying to define what a reduction is. And a reduction is a way of obtaining an algorithm for A. So that dotted box is an algorithm for A. It takes as input an instance. In other words, the parameters that an algorithm A would expect, like a graph or a set or whatever the algorithm takes as input. What it produces as output, I'll just go back. So it takes that as input. It either produces a solution that the algorithm is supposed to produce, or it says there's no solution. So this is an algorithm for a search problem. So you might put in a graph, and out the other end comes a Hamiltonian cycle for the graph, if one exists, or the algorithm reports there is no Hamiltonian cycle for the graph. Or it might take as input a set of integers, and it might produce as output a subset that adds up to some number, or it might report that there is no subset that adds up to that number. So we want an algorithm for A. And we happen to have sitting around an algorithm for some other problem B. And we want to leverage that. We just want to use it. We want to call B and let B solve our problem for us. And of course, B might not take the exact same inputs as A, and might not produce the exact same outputs as A. So you do this all the time when you program. You've got something that pretty much does what you need, but it's not exactly right. So what do you do about the input not being exactly the same? Yeah?
You manipulate it in some way so that it is.
Yeah. So you take the input that's intended for A, you pass it through F. That's just what we're calling, so F transforms the input into input suitable for B. And then maybe the output that B produces isn't exactly in the right form. And so when we get a solution to B, we run it through H. And that turns the output that was meant to be produced for B into output that's suitable for A. Okay? And if A and B are close to the same problem, F and H can be pretty simple. If A and B are radically different problems, you probably have to work pretty hard on F and H. And then finally, if there's no solution to B, we just report there's no solution for input I. Right? So to define a reduction for a problem A, you got to say, okay, I'm using an algorithm for B, and you've got to define F and H. So there's 3 boxes in there. constitute a reduction. This is called a reduction from problem A to problem B. And we looked at this example. So let A be the problem of finding a Hamiltonian path between two vertices in a graph. So the instance I is intended for A would be a graph. And what we want to see come out the back end is a Hamiltonian path. Well, actually, I need more specific. We're actually interested in specific vertices, and so the input would be a graph and two vertices in the graph. The output would be a Hamiltonian path between the two vertices, i.e. one that visits every vertex. It doesn't close the cycle. Now, we'll let B be a very similar problem. Let's suppose we have sitting around an algorithm that will find a Hamiltonian cycle in the graph. And we want to trick it into finding Hamiltonian paths. So those are both very simple problems. Right? And we want to do this reduction. So we want to figure out what F and H do we need. And we considered this problem. And right, there's the diagram again. So the input, as I say, is the graph G and the two vertices U and V. F adds a vertex X along with an edge from X to U and an edge from X to V. So it transforms the graph in that way. So it adds a vertex and two edges to the graph. And then H is going to see a cycle come out. And what it does is it removes X and its edges from the cycle that comes out. So it's not very complicated, but here's the picture. There's a graph. We want to know if there's a Hamiltonian path from A to B. Is there one? Yeah. Yeah, we can go here, 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 here. Yeah, I think that's not the only way. Okay? So we want to find Hamiltonian paths, but we're stuck with an algorithm that finds Hamiltonian cycles. And so the reduction is, we take the graph that came in, we add X with edges from A to B, and then we ask, find the Hamiltonian cycle. Now, if there's a Hamiltonian path in the original, will there be a Hamiltonian cycle in the new one? Okay, what's the argument? How do you know that if there's going to be a cycle in the new graph if and only if there's a path from A to B in the original, a Hamiltonian path from A to B? Yeah?
In order to create a cycle including X, A, and B, there must be two paths that connect A to B. One going through A, X, B, and the other going through the path.
Okay. So, if there was a cycle in the first place, if there was a path in the first place, there has to be a cycle, right? If there's a way to get from A to B, then there's going to be a cycle here that goes from X to A, back to B, and then to X. And if there's a cycle in this graph, clearly it's going to have to, at some point, go from B to X to A, the way we've constructed it. And so if we just take out, if you find the cycle, and take out that stuff, what you got left has to be a path. That's all the reduction is doing, yeah?
So any particular reason for adding as opposed to just an edge between A and B?
Okay, what's the problem with adding, instead of adding X like that, just adding an edge from A to B? That works for this graph. Okay. Why might it not work though? Why do you have to add that extra X? Yeah?
It doesn't work for this graph. Could it be that other graphs have more edges that are leading out?
Sure, but let's try to draw a graph for which that trick wouldn't work. Yeah?
Well, you need that extra X to force the route to go through there, because it has to visit every vertex. So like, you
Okay.
have that extra X that's forced to go through there, so you know A and B will both get that.
Okay, we've got to make sure that in the cycle that we get, well, here, I'll just show you the example first. Who could think of an example where it fails? Yeah?
Perhaps have some vertex C that leads to A. And then have an edge from C to B. And then from B to D. And then, actually, never mind a second.
That was
I lost it.
something
Okay,
about.
we're close. Let's do this. Okay? So the proposal was to have the reduction just to add an edge here. Then find a cycle, and then what do we do when we find the cycle? How do we recover the path?
Remove the edge.
Remove the edge from A to B. But what will happen if we find a cycle in this graph? So we do the reduction. We take the incoming graph, which is this. We add that edge. We go find a cycle. What will it find?
Cycle
There's only one cycle here, right? What is
ACB.
the cycle is A, C, B, D, A. Okay? And then, okay, so it found a cycle. Then to produce the solution to the original problem, we're supposed to remove the edge from A to B. There is no edge from A to B to remove. We didn't use the edge from A to B. And so the coming out the other end, we're kind of stuck. We can't produce the solution to the original problem. By doing it this way, with the new vertex, we know any cycle has to go AXB or BXA. And we know that when we remove, once we find the cycle, if we remove this from the cycle, what's left is going to have to be a path. Yeah?
So because that's already a cycle, when you create that X, it makes it impossible to visit all of them once?
No. Okay, let's add X.
No more cycle.
Huh.
Can't get to see.
Oh, okay.
But that would return no path,
Right.
which is true for this graph.
Yeah, okay, yeah. Okay, that graph does not have a cycle. I mean, does not have a path from A to B, a Hamiltonian path from A to B. If we add an edge, suddenly there's a cycle. Okay? When we add X here, there's no cycle, which is good. We don't want there to be a cycle because there wasn't a path to start with. So adding X sort of preserves what we want. If the original graph had a Hamiltonian path, this will have a cycle, and if it didn't, it won't. You can't say the same about just adding an edge from A to B. In this case, it flipped something that did not have a Hamiltonian path into one that had a Hamiltonian cycle. We don't want to go there. Okay? Any other questions about this? Okay, so that's our reduction. Okay?
Oh,
Yeah.
I have a question about the previous one.
Mhm.
So if you gave us an algorithm that finds Hamiltonian paths, can we reduce it to one that finds cycles? So the other way around.
Okay. So his question would be, let's reverse the roles. So instead of reducing Hamiltonian path to Hamiltonian cycle, go the other way around. What if you wanted to look for cycles and all you had were paths? So you want the big algorithm to be finding cycles, and you want to do it in terms of finding paths. Okay. Yes, you could. Rather than, I'll let you think about how you would do it, because I got another example I want to talk about instead. But yeah, in print, yes, you could find such a reduction. Okay. All right. Now, those two problems are very similar, right? Hamiltonian cycle, Hamiltonian path, and so maybe it's not so surprising you can reduce one to the other. But suppose that what you wanted was, you want an algorithm for the subset sum problem. Okay, and the subset sum problem takes as input a set of integers and a goal, which is another integer. And it looks for a subset of the set that adds up to the goal. All right? So suppose we want an algorithm for that, but all we had laying around was this weird problem. The problem of finding a path in a DAG that has a particular weight. So what we have is an algorithm for this DAG problem. So given a weighted DAG, find some path in that DAG that adds up to a goal. But what we want to solve is the set problem, the subset sum problem. Now they do have something in common. They have a goal. And one problem is a set of integers, and the other is integer weights. But somehow we got to take the set that's coming in, turn it into a graph, turn it into a DAG, a weighted DAG, solve the problem on the DAG, and then take the solution on the DAG, which would be a path, and turn it back into a subset of the original set. So they're very different kinds of problems. All right, I want you to think about that for a few minutes. So you're writing a program. In your library, you find an implementation of this DAG problem, and you want to use it. You want to leverage it to produce an algorithm for a subset sum. So in other words, I need a reduction. I need an F and an H. Right? Talk to the people around you. See if you can, I mean, how would you do it?
So,
Tell me
what do you we're trying to do the subset somehow.
Who has an answer, preferably a wrong one?
Preferably a wrong one?
Yes.
So our idea was to take the numbers in the set, basically, and turn them into a DAG itself. And so you weight them based on...
Okay, so for example, here's an example.
Right.
Here's our set. We want to find a subset that adds up to 13. So you're going to use the numbers to create a DAG.
Right.
Okay, so what specifically? Steph, point that at me. Yes.
And so it would have to be a DAG because, like, if you're going from 1 to 5, you're adding 5. But if you're going from 5 to 1, you're adding 1. And so you're trying to find, and you would connect every single one to every single one. And so you're trying to find a cycle that adds up.
Okay, well, first of all, we're not looking for cycles. We're looking for, there wouldn't be a cycle in a DAG.
Right.
All right, so how many vertices would I create here?
4.
Okay, so we're going to create one for each number. Okay, and then what?
And then you basically have a direction arrow. Well, no, it's acyclic.
You know, all right, so cycles aren't the issue. Okay, so, I mean, that's a start, though. What's your thought?
You could connect each vertex for the number that it represents in the set, connect it to all of the other vertices which represent the members that come after that.
I think that's a little fishy because the order of a set's not important. So I'm a little bit uncomfortable with that, but let's go with it. So what would you say? Connect this to what?
Connect that to every...
Well, first of all, what do you do with the numbers?
So the numbers are like starting values that you would have if you started at that vertex. And
Okay, but the numbers, okay, so the only place we can put numbers in this DAG are on the edges. Right? It's a weighted DAG, so I need a way to weight the edges. Okay? Yeah?
Then we need a fifth vertex then.
Need what?
We need a fifth vertex then.
Okay, you want a fifth vertex. And what do we do with edges? Yeah.
From the first vertex to the second, you have 4 edges.
Okay, one edge for each number up here?
No, no, what, just
From
from
just the first
just between the first 2 vertices.
4 edges. Okay.
Each of those is one of the numbers.
Okay, so 1, 5, 8, 9.
And then from the second to the third, take one of the edges off and repeat the process.
So 5, 8, 9,
Yep, and then just keep going.
and then 8, 9, and then 9. Okay, now what?
If there's a path,
Okay, so let me pick up for you. So that's his reduction. And now the idea is, let's suppose there's a subset up here that adds up to the goal. Will there be a path down here that adds up to the goal?
Yeah.
Okay, so for example, suppose 1, 9 added up to the goal.
Or 5, 8.
Then there's going to be a path 1, 9. So the argument you have to make is that for every subset up here, there's a corresponding path down here. And then for every path down here, there's a corresponding subset up there.
Would you need a lot more vertices to have all of the options?
Oh, I think this is enough.
Okay.
I mean, pick a vertex, like, take a subset up here, like 1 and 8. Yeah, there's a 1, 8. Or let's say it's 8, 9. Yeah, 8, 9. Yeah.
So what keeps you from doing like 9, 9, 9, 9?
Okay, so there's our problem. Is you can go 9, 9, 9, 9. So suppose someone said, is there a subset of this that adds up to 36? You reduce it to this problem of finding a path that adds up to 36, and you find one, but that doesn't correspond to a subset, so that doesn't quite work. Fortunately, you can make it work by making it simpler. Yeah?
Why did you choose 8, 9, or 5, 8, 9, 8, 9, and 9 to like finish out at the end? Were those just arbitrary decisions?
Yeah, he said we use them all for labels here, and then we take one away. I just picked one, yeah. 5, 8, 9. Then I took out the 5 and 9. Yeah?
So when you name a path in a DAG, don't you have to say like vertice A to vertice B? But like you don't have names for the vertices. So what is the?
Well, we don't even care, in the end, we don't care about the path that we find. We just want to know.
That it exists?
Well, I guess we would need to name them in some fashion, yeah. The names really don't matter, just we can name them uniquely. Yeah?
Do these have to be polynomial time reductions, or can we just like have a DAG for like every possibility?
Yeah, we have to be able to produce this thing in polynomial time. So we can't, you can't create a massively, exponentially large graph for this small set. Okay? I mean, all these are sort of getting at the right idea. Let's try a different approach. Why not? Now, there's no rule you have to start at the source and go to the sink. So let's just do this. Would that work?
Yeah. Well, you need more, right?
That's not going to work. If your goal is 13, it would. If your goal is 13, it would work. You'd start here and go there. Or if your goal were 10. There's no path that goes from 1 and then goes to here and goes to 9. Yeah?
Could you, for example, from the vertex from which you have the weight 1 edge, draw an edge to every other vertex with weight 1?
We could, but that would make a mess. I can do it more simply. What if I did it? I'm going to do the same idea. I'm going to do this.
Nice.
So I'll add these edges and weight 0. Now I think for every subset up here, there is a path down here. And for every path down here, there's a subset up there, if you take out the zeros. So like if you needed to, if you wanted to say, if your goal was 10, you could find the path. You go 1, 0, 0, 9, and it adds up to 10. Right? But there's an objection to this. Yeah?
This allows zero. Is zero an allowed answer?
If the goal is 0, suppose the goal is 0 up here. There is a subset up here that adds up to 0. And the path 0, 0, 0, 0 would work. So that when you're converting the path back into a set, well, how do you, suppose we find this, suppose the goal is 10 and we say, okay, here's a path here that adds up to 10. How would you turn that back into a set? Yeah, you would take the weights of all the edges, which is 1, 0, 0, 9, and take out the zeros and just produce 1, 9. Just throw away the 0 edges you take. Yeah?
So that would break if 0 was in your original set, right?
Well, it wouldn't matter. If 0 is in the original set, 0 doesn't, we can include the 0 or not in any solution we produce. We might as well take it out and make the subset smaller. Okay? There's an objection you could make. Yeah?
So it seems like you can't go back. Like when you go to that 9, has that edge, the weight is 9, then you can't go back to the.
Right, you can't go back, and that's a feature because we're supposed to be reducing it to a problem on DAGs. You can't go back on DAGs. The key thing you have to convince yourself of, if there's a subset up here that adds up to 36, or adds up to the goal, there will be a path down here that adds up to the goal. And the idea is, it's easy to see. If the subset contains some numbers, you use the path, you use the edge with their weights, and then you connect with the zeros as needed. Yeah?
Sorry, it's kind of like light switches. You're turning on the numbers that you want.
Right, if you want to use this weight in your subset, you take the edge. If you don't, you skip it and go via the 0. So you sort of pick which edges you want to use. And you also got to convince yourself that if there's a path down here that adds up to something, there's a subset up here that adds up to something. And I think it does. But I still, no one's made the objection yet that I'm expecting. Yeah?
I don't know if you addressed this already, but what if there are zeros in the set that you're given?
Yeah, well, if there are, any subset that adds up to anything, let's suppose that we ask, is there a subset that adds up to 17? And you say, yeah, it's 8, 9, 0. Well, just take the 0 out. There's also a solution 8, 9 that we found down here, so it's not really a problem. We can put zeros in, take them out all we want. Is this a graph?
Yeah.
There are 2 edges between these vertices.
It's a multi-graph.
It's a multi-graph, but I want a graph. In a regular graph, you can't have 2 edges between 2 vertices. How would you represent it? You know, you couldn't use our standard representation. So are we doomed, or is there a fix here? Yeah?
Just add another node?
Yeah. We'll just add an extra vertex here. We'll break each of these by putting a vertex. And where each of these edges is a weight 0. So now my picture has become kind of modeled, so I'll just show you the picture up here. Okay, so given that set, you produce this. So you got a set and a goal, you turn it into this graph in the same goal. You solve the problem down here. And then to convert out, when you find the path, the way you turn it back into a subset is you take all the weights on the path, throw away the zeros already. What's left is a subset of the thing up there that adds up to the goal. And if you can't find a path here that adds up to the goal, you just report there's no solution. So that's a reduction. That's a reduction from the subset sum problem to this made-up problem here. DAG path problem. Yeah?
So I'm curious, what was the intuition that led to making a graph to help solve the subset problem?
What was the intuition?
Yeah, why a graph? Sort of similar.
Well, I just invented this problem, just because I wanted a reduction between 2 very different problems, right? From a set of integers to a DAG. That seems, and it turns out that we're going to do proofs like this a lot to prove things are NP complete going forward. And a lot of times you have to reduce between very different kinds of problems. Right? So the first reduction was easy. This one takes some ingenuity to get. And if you look in your book, you'll find a whole series of reductions, some of which are easy to follow, and some of which you wonder, how did they ever conceive of that? And that's just the way it goes. Okay. Any other questions about this reduction?
Does it go the other way?
We could, yeah. We could take a DAG, an arbitrary DAG, not necessarily in this form, but it's possible. I don't know what the reduction would be, but given any weighted DAG, and the question is there a path in this DAG that adds up to a goal, you could, in principle, convert it to the subset sum problem. All right, now, we're not just interested in reductions, we're interested in reductions in polynomial time reductions. So a polynomial time reduction is one where this whole box requires polynomial time. So we want a reduction that has the following property. Assuming that this algorithm here takes polynomial time, we want to make sure that the whole pipeline takes polynomial time. So for example, if f takes exponential time, that's too long. We're only interested in reductions that can be done quickly, polynomial time reductions. Now, is that polynomial time reduction? How long would it take to take that set and produce this DAG? It'd just be time proportional to the length of the set, right? Because for every element up there, we're creating one of these triangles, basically. So that's not bad.
But do we have a way to solve that DAG in polynomial time?
Well, the requirement is that, assuming there is a way to solve B in polynomial time, the entire process will be polynomial time. And for that to be the case, we've got to have a fast F and a fast H. Now, what about the H for this problem? That takes the path and turns it back into a set.
You just include it and drop all zeros.
Yeah, that's just linear time as well. You just go through and take out the zeros. Okay, so let's think about what's required. Suppose F is polynomial time, O of n to the A, and B is O of n to the algorithm for B is O of n to the B, and H is O of n to the C. What bound can we put on the running time of the whole dotted line algorithm? If we're composing three polynomial time algorithms. One for F, one for B, and one for H.
Is it the max of A, B, and C?
Okay, is it the max of NB, of n to the A, n to the B, and n to the C? Or is it, another way to put that, is it n to the max of A, B, C? Or another way to put it, is it O of n to the A plus n to the B plus n to the C? All those are equivalent. Is that simple? Just add the complexities together? I mean, you're putting them together in a row, yeah.
Why aren't we considering n to the f?
Into the what?
F?
Well, F, we're assuming F is O of n to the A.
Copy.
Yeah, we are considering that. Yeah?
What does F spit out? Is it the same n as what we started with?
Okay, so Anthony has asked a question which is, how big, we have to know how big the input to B is. What if F takes input and produces an exponential amount of output? Now suddenly poor B is going to take exponential time in terms of the size of the original input. Do we need to worry about that?
Well, what the exponential would be.
Okay. Do we need to worry about F producing, suppose F takes input of size n and produces output of size 2 to the n. Then we're not going to have, so
Don't use that F.
but F, suppose F is polynomial time. F is O of n to the A. That's all we're going to require, is that F be polynomial time. But its output is of size 2 to the n. As a result, the rest of the pipeline takes exponential time just looking at its input. What do you say about that? Yeah?
How can an algorithm create more things than it has time for?
Exactly.
Well,
A polynomial time algorithm does not have time to produce an exponential. Right? How would it do that? If it could produce an exponential amount of output, it would take an exponential amount of time to do it.
well,
Yeah.
if you're counting like the number of bits, right, and then you're thinking about magnitude, so f produces, say, 4 bits, and then
I mean, it has nothing to do with, there's no trickery with bits here. It's just that, you know, if you got an algorithm that can make, that takes a small, you know, takes input of size 10 and produces 2 to the 10 marks on a piece of paper, it's going to take time proportional to 2 to the n, because you only write a mark each step. Yeah?
I think Anthony was asking, what if algorithm B reads the output differently than algorithm F?
I don't know what reading it differently has to do with it. I mean, it just, all we know is its running time is O of n to the b, where n is the size of its input. That's all that matters. So now, how much output could f produce? What can you say about the size of f's output? Yeah?
Can at most be the size of its input.
No, it could be bigger than its input.
it could be at most the size of its big O, like to the A.
F takes O of n to the a times, so its output is also O of n to the a big.
So you just multiply it all together and add up A, B, C.
Well, let's do it. So we're going to run f. So assume, so n is, you know, sort of a bound variable here. So let's let m be the size of I. So what comes into I, what comes into this box is the size m. So the first thing we do is you run f, and that's going to take O of m to the a time, and its output will be O of n to the a. So, you know, most m to the a. So now what can we say about the algorithm for b? How long is it going to take? What's the biggest its input could be? O of m to the a. And how long is it going to take? To the b. So m will run in O of m to the ab time and produce output of size O of m to the ab. And then what about h? At worst, it's going to be O of m to the abc time. We don't care about the size of its output. And so now what can you say about the running time of the entire box? These are the 3 stages. Yeah. First stage takes that long at most. Second stage that. Third stage that. So it's just O of that sum. But the thing to realize is these are each polynomials. So all I've done is argue that if the pieces are polynomials, you know, if f, b, and a are f, b, and h are polynomials, the whole dotted box will be polynomial time. So when I say let me say it again. F, b, and h run in polynomial time, so will the dotted box. You already believed that before I went into this excursion. I'm just showing you, you know, it's a little more, it's a little trickier than you think because of the size of the output question. Yeah?
Wouldn't it just be O to the n? M to the ABC? M to the ABC is the leading term, right?
Well, but maybe
C is 1/2.
maybe A, B, and C are all 1/2. So that would be m to the 1/2 plus m to the 1/4 plus m to the 1/8. In that case, m to the a would be the answer. So you're right. If A, B, and C are all greater than or equal to 1, it would be, the answer would be m to the ABC. Okay?
Can ABC ever be like negative?
Can A, B, and C be negative?
Like the bigger the problem, the faster it runs.
Well, we don't need to make that excursion. Okay, so this is called a polynomial time reduction, when f and the argument for b and the argument for h all run in polynomial time. And that's what we're interested in, is polynomial time reductions, fast reductions. Okay, now we can define a new set. So we have our set NP, which is the set of all problems that can be verified in polynomial time. Okay? And P is the set of all search problems that can be solved in polynomial time. And we saw last time, there are plenty of algorithms you can solve quickly, plenty of problems you can solve quickly. We've been studying them all semester. There are plenty of problems that can be verified quickly. Okay? Now there's a set NP complete. So far it doesn't say anything. The set of NP complete is a set of all NP complete problems, and you can say what incomplete is. So a problem from NP is also called NP complete if all other problems from NP reduce to it in polynomial time. So it's sort of, you think of an NP complete problem as being the master problem, the NP complete problems are the hardest problems from NP because all the other problems reduce to it in polynomial time. So what does that imply about NP complete problems? If you could pick any search problem, NP problems are search problems. You pick any search problem and you can solve it if you had an algorithm for an NP complete problem. You could solve it quickly if you had a polynomial time algorithm for an NP complete problem. What would it mean if you could find a fast polynomial time algorithm for an NP complete problem? Okay, yeah,
Then all of the problems would be solved by
Right.
polynomial.
That would mean that you could solve any problem from NP in polynomial time. Now, yeah,
Would this prove that P equals NP? Is that?
that would prove that P equals NP. Because suppose that we had an NP complete problem. Every problem from NP reduces to a polynomial time. And we found the polynomial time algorithm for that problem. Okay? How would that give us a polynomial time algorithm for the subset sum problem? How would that give us a polynomial time algorithm for the Hamiltonian cycle problem? How would you produce it?
For reduction?
Okay, you said the word reduction. Who else could tell me? What's reduction have to do with this? I have this mystery problem X, which is NP complete. How do I know, if X has a fast solution, how do I know the subset sum problem has a faster solution? What do reductions have to do with it? You've had your chance. Yes?
If you can reduce the mystery problem to X in polynomial time?
Okay, I'm not sure what the difference between the mystery problem and X are.
No.
Okay. Let's let X be the NP complete problem. Okay? And we have discovered a polynomial time algorithm for it. How do we know there's a polynomial time algorithm for subset sum? Yeah.
Transform the subset problem into an input to the NP complete problem. And
Right.
transform the output of the NP complete into
Right.
the solution.
By definition, every NP complete problem, any problem from NP can be reduced to an NP complete problem in polynomial time. So that means if I've got this problem X over here, which is NP complete that I can solve quickly, I can take any problem from NP, say the subset sum problem, reduce it in polynomial time to problem X. And we have just showed that when we do that reduction, we come up with a polynomial time algorithm for the subset sum problem. Yeah?
Don't problems in NP produce, or can problems in NP produce exponential output though? So wouldn't the input to the NP's complete problem?
Well, what I'm saying is, let me go back to the picture. Suppose B is an NP complete problem, and we discover a polynomial time algorithm for it. By definition, every problem from NP can be reduced to X in to B in polynomial time. So if we have a polynomial time algorithm for B, there has to be a reduction, so it means we have to be able to find an F and an H that run in polynomial time. That dotted box would now be a fast solution to any problem from NP. We could produce that way. Yeah?
When you say you find an algorithm that can solve, do you mean solve it or verify it?
Solve.
Solve.
Right. Yeah.
So I'm really confused. Does this mean that the NP complete set is empty?
No. Does not mean the NP set complete is empty. It's not close to empty.
But you're saying that to be NP complete, that there's an algorithm.
To be NP complete, there has to be a way to reduce any problem from NP to that problem
In polynomial time?
Oh.
in polynomial time. I did not say that a polynomial time algorithm for that problem had to exist. What I said is if you could solve one of these NP complete problems efficiently, you could solve every problem from NP efficiently. But no one has ever found a fast way to solve any NP complete problem. But if we could solve one of them, we'd be in business. Yeah?
Well, the NP complete problems
Okay, if you solved one NP-complete problem, could you solve all the rest efficiently? Why?
By definition, NP-complete problems can be reduced to other NP-complete problems.
Right. NP-complete problems are also members of NP. So every NP-complete problem can be reduced to every other NP-complete problem. Yeah?
It's not kind of a circular definition.
It's an equivalence class, so.
A circular definition? No. We know that any problem, let me see if I can find a, I don't have to draw in the air here. There you go. Let's see, NP complete. Okay, this is the most likely scenario of the way our world is organized. NP is this outer circle. P is this inner circle. The hardest, think of the NP-complete are this set in this annulus here. So the NP-complete problems are part of NP. I put them, my intuition I want you to have is the further you get out from the center, the harder the problems get. So think of the NP-complete problems as being the very hardest problems in that set NP. So 3 is an NP-complete problem. Since it's an NP-complete problem, by definition, that means that every other problem in this set reduces to it in polynomial time. So 1 reduces to 3 in polynomial time. 2 reduces to 3 in polynomial time. 4 is here, it'll reduce to 3 in polynomial time. 3 will reduce to 4. Yeah?
So 2 is the set NP but not NP-complete?
Well, everything inside this circle here is a member of NP but is not NP-complete. So these are the problems that can be solved in polynomial time. Right? Those are the ones we've solved. Now, there are lots of other problems that are a member of NP. Some of them have been proven to be NP-complete. And then there are problems in between that for which we do not know a polynomial time algorithm, but which we have not proven are NP-complete. There's a very famous problem sitting right there, in fact. Okay? When you think of a problem, I'll just tell you, it's factoring. Okay, the factoring problem is a search problem. It's a member of NP. It has not been proven to be NP-complete, but no one has ever found a polynomial time algorithm for factoring. And I've told you before, if we could find a polynomial time algorithm for factoring, it would crash RSA. RSA would be easy to crack. So, if someone could prove that factoring is NP-complete, what would that mean? Yeah?
RSA is invincible.
It wouldn't mean RSA is invincible, but it would mean RSA, it's very likely that there is no efficient way to solve. Okay? Because all these NP-complete problems, the best algorithm anyone has ever found is exponential for any of them. But if you could solve one of them, you would solve them all. So we'd be more comfortable with RSA if we could move 2 out here. Yeah?
With the advent of quantum computing and efficient ways to solve factoring, if factoring was NP-complete, would that mean that you could solve any exponential or greater, like an NP problem in polynomial time on a quantum computer?
That I don't know.
Okay.
But on a quantum computer, yes, there are fast factoring algorithms on quantum computers for factoring, obviously. There are no quantum algorithm has ever been found to solve an NP-complete problem efficiently, which is why people think 2 is probably not, that factoring isn't NP-complete, but that's not a proof. Yeah?
So how do you know if an algorithm, if every NP problem, okay, how do you know if an algorithm is NP-complete? Like, because there are algorithms that we haven't discovered, or that, there are algorithms that have not been defined yet, and we have to say that
Okay.
they reduce to NP, to that.
Right. So what he's saying is that to prove something's NP-complete, we got to show that every problem from NP reduces to it polynomial time. But there are an infinite number of such problems. How do you do that proof? That's where we're headed. Let's do one last question.
I also had a comment. I was going to say so these problems that are not
class of problems referred to as NP intermediate.
So you're saying that if P is not equal to NP, then this set here is not NP.
Yes.
The other possibility is,
Can you repeat that?
he's saying that if it turns out that P is not equal to NP, then that means that these all require exponential time. These require polynomial time. But there'll be some in the middle that are not NP complete but still require exponential time. The other possibility is that P equals NP, and all these distinctions are unimportant. That everything can be solved quickly. Okay? So let's take a break and we'll look at showing that things are NP complete. All right, let's get started again. Okay, now, I'm having trouble pronouncing the word polynomial so many times, so I'm going to stop saying it. When I say reduces to, I mean reduces to in polynomial time, unless I say otherwise. All right, don't be snowed by this. You know, it's easy to just turn yourself off and just decide that this is impenetrable. It's really not that complicated. It's just a little bit of terminology. So NP is a set of all search problems. And a search problem is one that can be verified in polynomial. It can be verified in polynomial time. Okay? So NP are the ones we can verify quickly. P are the ones we can solve quickly. Clearly, P is a subset of NP. If you can solve it, surely you can verify it quickly. The question is it a proper subset? It may be that every problem that can be verified can be solved quickly, or it may not. We don't know. Some compelling evidence that you cannot solve every search problem quickly is the existence of NP-complete problems. And think of NP-complete problems as the hardest problems from NP. And the way they're defined, they have a property that if we can solve one of them quickly, that implies we can solve every single search problem quickly. And that, together with the fact that there are thousands of problems that have been proven NP-complete, seems to suggest that we can't solve every problem from NP quickly. Because surely by now, if there was a way to solve one of these NP-complete problems quickly, we would have found it. Okay, so NP-complete, the way it's defined is, it's a problem from NP to which all other problems from NP reduce. That's our definition of hardest. So you pick any problem from NP, there's a way to reduce it quickly to an NP-complete problem, or to any NP-complete problem. So that means that all those problems there are examples of NP-complete problems. Now, there's sort of an asterisk here. we're talking about search problems, so we have to talk about the search versions of these things. So for traveling salesman, for example, that's not a search problem, it's an optimization problem. So in this case, we're talking about finding a Hamiltonian cycle with a total weight less than or equal to something. So there's search versions of these optimization problems. Okay? So all those are known to be NP complete, along with many, many others. So, and then that's the picture we just saw. If P is not equal to NP, this is the world. Problems we can solve quickly. The hardest problems, which we can't solve quickly. And then in between, there are going to be some of these problems that are in between. Maybe someday we'll find a fast way to solve them. Maybe someday we'll prove that some of these take exponential time. And, but no, that set would be non-empty. Okay, so these would definitely require exponential time though, if P is not equal to NP. Or this could be the situation, which looks about the same. Oh, P and NP are the same. Everything in here can be solved in polynomial time. That's the other possibility. Yeah.
So I want to clarify the definition of NP complete. So it's not part of the definition that NP complete problems run in exponential time.
No.
It's that but it's just by chance that all of them that we know of run in exponential time.
Yeah. The NP complete problems are the very hardest ones from NP. After all these years, no one has yet found a fast algorithm to solve any of them. Which is why, if you had to bet, you would bet that these actually do require exponential time. Yeah?
So just to be clear, like the reduction can't go either way, right? It can go like from the inner circle to the outer circle.
Well, the definition is that any problem from this set reduces to every problem in this annulus. It doesn't go the other way. You can't take, say, the traveling salesman problem and reduce it to finding the largest number in an array. But you can take finding the largest number in an array, that's a search problem. But anyway, you can take a simple array algorithm and reduce it to an NP complete problem.
Go like to the other.
Right, you can reduce easy problems to hard problems. You can't reduce hard problems to easy problems. That sort of makes intuitive sense. Okay, so these implications are things I've been discussing. If we discover a polynomial time algorithm for any NP-complete problem, everything collapses. P equals NP. Right? Because if I can solve the subset sum problem in polynomial time, I can then, now I have a fast algorithm for that. I can take any problem from NP, convert it quickly into the subset sum problem, because that's what it means to be NP-complete, that there's a quick reduction to it. Then I solve that subset sum instance, and I have a solution to the original problem. So if I can solve one of these guys, I can solve them all. If P is not equal to NP, that implies that all these NP-complete problems actually require exponential time, which is what what is probably true. But so far, the proof that P is not equal to NP has not been found, and the algorithm that would show that P equals NP has not been found. So it's an open question. Yeah.
Do you think it's likely with advancements in technology that the NP-complete problem model will be opened up and then we'll be able to crack all these crazy ones with it?
I don't think, personally, I don't think it's likely. I mean, armies of programmers for 70 years have been writing programs, and no one has, it would seem that there was a fast way to solve one of these problems. Somebody would have come up with it by now. Yeah?
I feel like in terms of history of science, 70 years isn't really all that long.
That's true. But the way I think about it is, people have been working on these problems longer than I've been alive. That seems like a long time. Okay? So, how do you prove that a problem is NP-complete? Well, it says right here. You take some problem that you know is NP-complete and reduce it to problem X. Okay? Why would that show that, why would that work? You take a known NP-complete problem you got some problem X that you want to show as NP complete. So what you do is you take an NP complete problem and reduce it to X. How does that show that X is NP complete? How does that show that every search problem reduces to X? Yeah?
Hang on, wouldn't you take X and try to reduce it to the NP complete problem?
No. It is no big trick to reduce something to an NP complete problem. Right? You can reduce trivial problems to an NP complete problem. The question, why does it work to do that other reduction? Yeah?
Because everything already reduces to the, for every problem in NP already reduces to the NP complete problem, so if you reduce NP complete problem to X, then that's
Right. So we have this known NP complete problem. That means everybody reduces to it. And then if we can show how to reduce it to X, we can just compose the reductions. Okay? There will be a question on the final similar to this. When you're proving something's NP complete, do you reduce the known NP complete problem to X? Or do you reduce the other direction? And the answer is you reduce the known NP complete problem to the candidate, not the other way around. People like to get that backwards. Yeah?
So how do you prove the first one?
Ah, thank you. Okay. So in 1970, there was a professor at Cal, UC Berkeley, that proved the original, did the original proof of NP completeness, proved that a problem was NP complete. Invented all the terminology, conceived of the notion of NP completeness, proved that a problem was NP complete, and then started proving that other problems are NP complete. So the proof of the original NP complete problem we'll get to eventually. But once he had defined that field, a lot of work started and lots of other problems were proved to be NP complete by reductions. So the first one wasn't done by reduction, obviously. It had to be done a different way. Now, Cook, for his trouble, was denied tenure at Berkeley. So his work wasn't appreciated at the time. And so he went on, I don't know if he's still, he went on to Toronto, University of Toronto. May have retired by now, I don't know. So he started this really famous, important field that at the time it was not appreciated. Yeah?
How do we know that this notion of NP completeness is actually useful? Like that this is how we're going to make algorithms more efficient?
Well, it's not how we're going to make algorithms more efficient. This is Cook's contribution. At the time, 1970, there were all these problems out there, you know, traveling salesman problem, whatever, that people had not been able to find algorithms for. And what he showed was, it's unlikely you're going to find algorithms for them because they form this equivalence class of NP-complete problems that are all reducible to each other, and solving one is tantamount to solving them all. So before it was like every one of these problems people could work on and not realize there was connection between them. He showed there was this important connection between them. It makes it unlikely that any of them can be solved. Yeah.
This is probably a stretch, but is there like a word relationship between the term NP complete and like Gödel's incompleteness theorem for math? Like, or am I just?
It's a different sense of completeness. Yeah. Okay, so let us look at proofs of NP completeness. Okay, now beginning of this is going to be similar. So this is just defining the sets. So you've already seen those words. These are known to be NP complete, at least the search versions of them. These actually belong to P. Those are things that we can actually solve. Again, the search versions of them we're interested in. So we got these two sets. And this is the idea about proving NP complete. If you know X is NP complete, the way you prove Y is NP complete is you give a fast reduction from X to Y. Now, to be NP complete, we have to show that any problem from NP reduces to Y. Well, since X is NP complete, we know that every problem from NP reduces to it. This reduces to that. So if you just compose the reductions, just call one after the other, you can convert A into Y. You can convert E into Y. Now, if sometime in the future one of you discovers a fast algorithm for Y, we'll just dig up those reductions that we know to exist that had to be found to prove NP completeness and go to work, applying these reductions and getting fast algorithms for everything else. Yeah.
So if anybody found a Y, that would break RSA and everything else, because
Yeah, and
NP complete.
right, factoring reduces to y, reduces to an incomplete problems, right? So, now, typically, more often than not, when I give this lecture on NP completeness, someone comes up after lecture and says, during lecture I came up with a fast algorithm for the subset sum problem or something like that. And I usually look at it and rather than try to figure out whether it's right or not, I just say, go implement it and then report back. Time it and tell me what happens. And I never hear back. So I don't mean to discourage you from approaching me, but it's easy to be fooled into thinking you solved the problem. Yeah.
So does this same equivalence apply for P and NP? If say some X, you want to say is NP, you just reduce it to another NP, or P, and reduce it again to another P?
Okay, you have to be careful when you use the word NP and the word IN at the same time. And I think you were mixing them. I never say, is some problem in NP. I say, is some problem belong to NP. That's a long way of saying I don't understand your question.
Okay, so for this tour,
Yeah?
you want to know if X is NP complete. You just find a way to reduce it to another thing in the set. So that way you know.
No, the question we're asking is why NP complete?
Right. Prove that.
So we find an NP complete problem that's known to be NP complete, and we demonstrate there's a reduction in that direction.
Right. So that way they're both in the same set.
So they're both NP complete, yeah.
So could you use that same logic in NP set and in P set to say if you have some random thing, you can reduce it to a known NP problem, then it's NP as well?
Yeah. So assuming it's a search problem at all.
So how about going from y back to x? Like, don't we want to be able to go back and forth in this graph? So if someone solves x
Yeah.
to be...
We already know you can reduce y to x. So he's saying we've shown this reduction to x to y. Well, y also has to reduce to x, right? Because any problem reduces to x. But y is already on this side. Every problem from NP, including y, reduces to x. Right? So we have the back. So any NP complete problems, they can be inter-reduced to each other, either direction. Okay, there's our picture of polynomial time algorithm. Okay, so what was this a proof of? Suppose I tell you, we did the reduction of the subset sum problem to this weird DAG problem. We know that the subset sum problem is NP complete. So when we demonstrated this reduction, what did we prove? Yeah?
That weird DAG problem is also NP complete.
This weird DAG problem is NP complete. So that was a proof of NP completeness. So the existence of this reduction, together with the fact that the subset sum problem is NP complete, proves that this problem here is NP complete. Now, back in the day, in Cook's, in the heyday, in the early 70s, people wrote PhD dissertations proving NP completeness of various problems. Now it's not unusual to go to a high school science fair. Well, I don't know how. It's a typical thing that shows up at some high school science fairs now. Say a math or a computer science thing, proving some problems NP complete. Why has it gotten easier to do? Why did it used to be so hard to prove something is NP complete? And now it's easier. Yeah.
We know of more NP complete problems to do the reduction.
There are just more NP complete problems known, and so if you've got to do a reduction, it's likelier you're going to find something close to what you need. But when there was only one NP complete problem known, you didn't have any choice. You had to take that problem, which is the satisfiability problem, 3-SAT essentially, and find a reduction to something very different. Yeah.
So it says it's a polynomial time reduction?
Yes. Yeah, all the reductions have to be polynomial time.
So,
yeah.
How is that initial problem proven to be NP?
All right, so I got the question again. Where did this initial problem come from? We're headed there.
Okay.
Yeah?
So how do we know that not all NP problems are NP complete? I guess that's stupid. That's a stupid question.
Yeah, some problems are just so simple that it's obvious you can't do a reduction from every problem to it. Okay? So this is just summarizing what we're talking about. basically, if there's a polynomial time algorithm for some NP complete problem, then P equals NP. So if you can solve one of these, you can solve them all. And if you can show that one of these NP complete problems requires exponential time, they all do. All the NP complete problems do. So either all the NP complete problems can be solved quickly, or none of them can. And that was Cook's insight. All right, and this is what we've been talking about as well. To prove an NP complete problem, you reduce from the known NP complete problem to the suspected NP complete problem. Okay? Now, in 1410, I have my students, I drill into them that this, the keyword this, in Java, is the object on which the method was invoked. All right? And I tell them that it will be on the final, and I do this over and over again, and people miss it on the final. Okay? So in this class, what I drill is you reduce from the known NP complete problem to the suspected NP complete problem to prove the suspected one is NP complete. That's the direction. It is not the other way. People will miss it.
Maybe you should stand on it.
Maybe I should stand on the table. But I've already done my standing on the table for the semester.
We never forgot.
Yeah, you'll remember that. All right, so we will, we're almost ready to talk about how you prove something. The original problem is NP complete, but alas, you have to wait 2 days to find it.